Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. Hello viewers, this is the second video of this coursework. It is a simply supported beam with uniformly distributed load at a specific location, right? Let us see the statement of the problem. A simply supported beam of 6 meter length is carrying a uniformly distributed load of 5 kN per meter over a length of 3 meter from the right end. Draw the shear force diagram and bending moment diagram of the beam using ANSYS mechanical APDL and compare the results. We have to compare the results because we are already getting the results from the question paper itself. It is having maximum bending moment of 12.66 kN meter, and also you can see maximum shear force is 3.75 kN, minimum shear force is 11.25 kN. Right? We need to analyze this one using ANSYS mechanical APDL. Then after analyzing, we need to compare the results, right? So without wasting time, let us start the problem. In all cases, we will consider modulus of elasticity of the material equal to 2 into 10 to the 11 Newton per meter square, and Poisson's ratio is 0.3, and cross section of the beam will be 0.01 meter by 0.01 meter. It will be a square cross section of 0.1 meter by 0.1 meter. Okay. And here in this case, you can see total length of the beam equal to 6 meters. So without wasting time, let us start our analysis. First of all, we need to create a directory, and in that directory, we need to save everything, right? And next to that, we can provide a title of this one as FEA 2. Okay. To see the title, we can click plot replot. It will show the title at the lower left corner. So this is visible, right? First of all, we need to select what type of analysis it is, and it will come from preferences. Definitely it is a structural analysis, so structural analysis checked in. Okay, next to that we need to provide elemental properties, and that will come from preprocessor. Element type, add, edit, delete. We need to add the element. Let us select beam element with 3D finest strain, and element type reference number is 1. Okay, and from options we can select element behavior as cubic form. Okay, let us close it. Next to that, we need to provide material properties, and we already told that for all cases we will consider modulus of elasticity as 2 into 10 to the 11 Newton per meter square, and Poisson's ratio as 0.3. So material models: structural, linear, elastic, and isotropic. Modulus of elasticity will be 2E11, that is 2 into 10 to the 11 Newton per meter square, and Poisson's ratio is 0.3. Okay, let us close it. Next to that, we have to provide a section of this one, and it is a square cross section of depth and breadth equal to 0.1 meter by 0.1 meter, right? So sections beam cone sections breadth equal to 0.01 meter and height equal to again 0.01 meter. Okay, done. Next to that, we need to start modeling. Model, create key points. We need to create key points in active coordinate system. Total length of the beam is 6 meter, and we need to provide uniformly distributed load from the middle of this beam to the extreme right hand side. So let us create a node at the origin. By default, it will take the origin location, so apply. Next node will be created at a distance of 3 meter, apply, and the third node will be at a distance of 6 meter, apply. We have provided 3 different nodes: node 1 at origin, node 2 at the middle, that is at a distance of 3 meter from the left hand side, and node 3 at a distance of 6 meter from the origin. And again, for orientation, we can provide another key point at any specific location. Suppose we are providing the key point at a distance of x equal to 0 and y equal to -3. So this is the key point for orientation, right? Now we need to provide lines. We have to create lines with these key points, right? Lines, straight line. Let us join key point 1 and 2. Done. Again 2 and 3. Line is made, right? Okay. Next to that, we need to create meshing. And before meshing, we need to select mesh attributes, because we have created one extra key point that is for orientation of the beam, right? Now let us select all lines, and we can select key point number 4 for orientation. Okay. Now let us select orientation point again 4. Okay, done. Now we can start meshing. It will be started from size controls, manual size, lines, all lines, and let us keep the numbers of elemental division equal to 10. For each line we will make 10 numbers of divisions for each line, so it will be having total 20 numbers of elements. Done. Now we need to mesh it. Mesh lines, pick all. Meshing is complete. Done. Now we need to apply our boundary conditions from here. Load, analysis type, new analysis. It is a static structural analysis, and we need to define loads, right? And from left hand side it will be fixed. It is a simply supported beam. Define loads, apply structural displacement on key points. Let us select node number 1, apply. It will be restricted to move in X, Y, Z direction. By the same time it will be having restricted rotation along X and Y. Only it is allowed to rotate along Z. Apply. Next one, at third key point, selected. Okay. Here in this case it will be a little bit different. It will be restricted to move along Y axis, Z axis, and restricted rotation along X and Y. Okay, done. Now we need to apply a load. It will be uniform distributed load from the middle of this beam up to the extreme right point. Let us see that drawing again. So load to be applied 5 kN per meter from middle point to the extreme right hand side. Okay, it will be applied in the form of pressure, and to see the exact location we can see in the form of lines. We can see the elements in the form of lines only. Plot lines. So from here to here it will be having uniformly distributed load, right? So structural pressure on beams, we can select the specific nodes by box. All the specific nodes are selected. Okay, and load key number is 1, and pressure value will be, it will be for downward direction, it will be -5000, and it is constant. It will be same for the last node also, -5000. Okay, done. We can see we have applied a uniformly distributed load of 5 kN from the mid of this beam to the extreme right hand side. All our boundary conditions are applied. Now we can solve it. From solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. We can see our results from general post processing. Okay, general post processing. First of all, we will read the results, and it will be read from the last set. Done. Now to see the bending moment diagram and shear force diagram, we need to plot element table. It will come from element table, define table. We need to add it. For bending moment diagram, we need to select numbers 2 and 15, right? So it will be from drop down menu, we can select by sequence number, and it will be SMISC 2. Apply. Done. First one. Second one, again we need to do the same thing. From drop down menu we can select by sequence number, and from SMISC it will be 15. So 2 and 15 will provide bending moment diagram. Okay, and for shear force diagram we need to provide different numbers 5 and 18, right? Again repeat the same process. From drop down menu we can select by sequence number, and SMISC it will be 5. Apply. Like in the last one, by sequence number selecting, and from SMISC it will be 18. Okay, we have selected the specific numbers. For bending moment we need to select 2 and 15, and for shear force you need to select 5 and 18. Close it. First of all, we'll see results from listing, list results, and we'll see reaction at the supports, right? So reaction results or reaction solution, all items you can see, it is showing that reaction at node number 1 Along y direction it is 33.75 kilonewton, and at node number 22 it is 11.25 kilonewton. We can compare these results from actual results. Let us see that one. It is showing that at node 1 it is 3.75 kilonewton, and last node it is 11.25 kilonewton. We can compare this. It is 3.75 kilonewton at node number 1, and at last node it is 11.25 kilonewton. So reaction force at the supports or at the ends are validated. Next to that, we need to see our results from maximum and minimum bending moment. That can be viewed from elemental table data again. You can select all the numbers SMIC2 and SMIC15, that will provide bending moment diagram, and next one SMIC5 and 18, that will provide shear force diagram. We'll see all this together, right? Let us see all these things. This is the results, right? Let us see it. At different nodes you can see the different results, right? And you can see here, like first one is actually, you can see SMIC2 and SMIC15. This is actually bending moment. These two are actually bending moment, and these two column is for actually for shear force. So maximum bending moment is occurring at node number 13. It is 12.6 kilonewton meter, and at node number 12 also it is same thing. It is 12.6 kilonewton meter. Maximum bending moment is 12.6 kilonewton meter. It is occurring at node number 12 and 13. And again you can see for shear force, maximum shear force is occurring at node number 1. It is 3.75 kilonewton, right? Maximum shear force is occurring at node number 1. It is 3.75 kilonewton, and minimum is occurring at node number 20. It is minus 11.25 kilonewton. Minus means it is in the downward direction. Maximum shear force is 3.75 kilonewton and minimum is 11.25 kilonewton. That one we'll see it from the drawing again, right? Let us see that. We need to see plot results. Can do plot line elemental response, and you will see from here, from bending moment you need to select SMIC2 and 15. Let us see. And for see the results in an expanded view or in a zoomed view, let us increase the scale factor from 1 to 2. Let us see the results. You can see here maximum bending moment is 12.6 kilonewton meter at this location and this location at two different points. And here you can see, here it is 11.2 kilonewton meter, right? And minimum is, here it is, you can see minimum is actually minus 0.261 into 10 to the minus 7. It is approximately 0 minimum, right? At different location you can see it is different. Let us compare this one from our results again. See what we got. You can see maximum is 12.66 at this location, and next higher value is actually here at this location. It is 11.25, 12.66 and 11.25. Let us see that one. Here it is 12.66. You can see maximum is 12.66 and next one is, you can see 11.2. Maximum is 12.66 and next one is 11.2. So these are the results. So this is validated with our question paper. So this is exactly same thing what we got in our question paper, that is completely validated by ANSYS mechanical APDL. Next to that we'll do something else. We'll see the animation of this model, and before that we need to see the 3D model that can be viewed from plot controls, style, size and shape, and from there display of elements should be on. Okay, done. And let's plot the elements. This is the thing. You see this is very thin one. So this is the beam actually, right? You can see this is a specific cross section. It is having cross sectional areas of 0.01 meter by 0.01 meter, right? Now we want to see the deformation of this one by the loads. You can see in the form of animation, right? Plot controls, animate, deform results. Okay, let us see the deformation. Let us decrease the delay. You can see how it will be animated, and also together that you can see the deformation along y direction, how much will be the deformation at each point also that can be viewed, right? Let us close it and we'll see the deformation, right? Let us see that one again. So nodal solution, and we'll see DOF solution and y component of displacement. You can see this is the displacement. You see maximum displacement is actually 255.061, right? So this is the displacement diagram, displacement of different nodes. To see the displacement of each node, we can see the listing results, right? Listing results, nodal solution, DOF solution, and y component of displacement. Let us see the displacement of each node. Maximum displacement is occurring at node number 23 is 255.06 at node number 23. Okay, this is all about our today's video. This was very simple finite element analysis of a simply supported beam with uniformly distributed load. We validated our results with the problem provided, and we got the exact results what was given in the problem, right? So with this one, we conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.